So in conclusion, for the kinematics, we're going to stay with the independent suspension type using an unequal, non-parallel air and geometry. 4130 chromoly round tubing. We will make some geometry modifications to accommodate for the new chassis and also for a redesign of the uprights. And we'll stay with the steel alloy bearings where the outboard and run ends inboard. And as you can see, I want it to be noted that there are ways that we could change the kinematic system. But our decision to change the uprights was appropriate for us. And to prove that, we went ahead and basically weighted against all of our goal criteria. So we're very confident that the way that we're going to go with this matches our criteria and is advantageous to us. And with that, I would like to turn the floor over to Carlos Flores to discuss the steering system.
Thank you. Good evening. I'll be talking today about the steering system. The main idea behind the steering system is to transfer the rotational displacement of the steering wheel to a linear displacement of the tie rod, which in turn turns the wheels. It also provides the feedback or the handling to the driver, which is very advantageous for a suspension system. So basically, the goals for a suspension system are to optimize the angle of inclination, optimize the steering ratio, and at the same time, try to reduce the deflection in the steering rack. Before we start, let me show the components. Number one, we got the steering wheel. 2, U-joint. 3, steering column. 4, Piedmont arm. 5, tie rod. 6, the rack and pinion mechanism. 7, and the rack mount. The steering mechanisms that were considered were the rack and pinion mechanism and the recirculating bolt. The rack and pinion mechanism is a lightweight system which provides a quick steering ratio, which is ideal for applications. It also helps minimize bump steering. On the other hand, the recirculating bolt mechanism involves many parts, creating the system heavy and does not provide a quick steering ratio. As an example, bicycles and motorcycles use a 1-to-1 steering ratio. Automotive vehicles use around 12 to 25 to 1 steering ratio. For purposes in the past, we have used 4.16 to 1 ratios. So we're trying to look to aim for that. Also, the steering geometries that we considered are the Ackermann geometry, the anti-Ackermann, or the parallel geometry. The Ackermann geometry is good for purposes due to the fact that if you look at picture A, the front wheels turn at different angles, allowing the inside front wheel to turn more than the outside wheel. This allows to give small, tight currents at low speeds. On the other hand, if we use the parallel geometry, as seen in picture B, we see that both wheels are turning at the same angle. That is ideal for long-term radiuses, which is not ideal for applications. Mostly it's used for high-speed racing, such as professional Formula race cars. Therefore, our steering design proposals are to use the rack and pinion mechanisms due to the fact that it meets the growth criteria. It's a lightweight system, and one of the advantages of this system is that we could buy this instead of manufacturing in-house, which would help to have an early finish of the vehicle. At the same time, it optimizes the steering ratio and maximizes handling. On the geometry, the Ackermann geometry will be used since it also meets the goal criteria. It optimizes our steering geometry. It's suitable for slow turning, small radius turns at low speeds, and therefore it's ideal for applications. Now I would like to turn the floor to Greg Miller, who will be talking about kinetics.
Thank you, Carlos. What is kinetics as it relates to the suspension of a vehicle? Where kinematics is often described as the geometry of motion, kinetics looks at the unbalanced forces and their resulting changes in motion. What does this mean? Well, without suspension, the force of a bump from an uneven road surface will set the vehicle into motion away from that road surface. Anytime the wheels leave the road, the driver is no longer in control of the vehicle. With suspension, the springs store the energy transmitted through the push rods and belt crank mechanism. Some of this compression energy is absorbed by the fluid in the shock absorbers and released as heat energy. But the portion stored in the spring will push back in the other direction as the spring unloads and rebounds. Again, energy is absorbed by the shock, allowing the wheel to stay in contact with the road surface without slamming into it or causing the vehicle to bounce up and down endlessly. The anti-sway bars are also a type of spring, and their job is to resist body roll. The kinetics components consist of the springs, the shocks, the belt crank mechanism, the push rods, and the sway bar, which is connected through these linkages here. Last year's team was very successful in achieving their kinematics design goals. This year, the goals in kinetics will be to improve reliability, to continue to provide excellent handling, to reduce braking nosedive, and to minimize body roll. Linear springs are readily available. They simplify the dynamic calculations due to their constant rate. One possible drawback, depending on how they're utilized, is that they could cause the vehicle to bottom out. This year we're planning to run the Cane Creek adjustable fluid shocks. They have proven flexibility and effectiveness on last year's vehicle. One of the most important aspects of tuning is the ability to do it easily on the car at the track. There are 4 independent adjustments: high and low speed compression and high and low speed rebound. These adjustments are easily made using simple tools. These shocks include a coilover spring for a very compact package. Using a belt crank system provides many advantages over placing the spring directly along the spring axis. Some of those advantages are designable, smooth rising wheel rates utilizing mechanical advantage and allowing for more packaging options. Belt cranks also optimize shock and spring performance by utilizing more spring travel through relatively small wheel travel. They are relatively easy to manufacture from steel and aluminum, but would be much more difficult, time-consuming, and costly to manufacture from carbon fiber. Although their packaging arrangement does raise the CG height, push rods simplify the location of shocks and belt cranks in that the shocks and springs are located on top of the vehicle, which allows for easy adjusting and tuning.